Okay, it's a great pleasure to open the scientific part of this conference. So let's in fact the speakers, the participants, and my co-organizer, in particular local co-organizer, Marco, Jacopo, Stefano, and the others, Claudio, and more. But Marco, a big thanks, and others. Now, I want to give my thanks also to the staff of Centro De Giorgi. Many thanks. It's a great pleasure now to introduce Andrea Malchiodi from Scuola Normale Superiore of Pisa. Andrea will talk about sharp bounds on the Nusselt number in Rayleigh-Bénard convection. Andrea, please.
Okay, thanks for the introduction. And yeah, maybe I would like to say first a few words about Anna Maria and Vieri. So they're colleagues that I heard of when I was already a student, and then I met. So they're great mathematicians and wonderful persons. So it's really great to be here to celebrate them. So. All right, and of course, I'm grateful to the organizers also for inviting me here. So I would like to discuss some joint work with Sagun Cianillo from Rutgers about a problem in fluid dynamics. And this is about the so-called Rayleigh-Bénard convection. So the setting is the following. There's a fluid in a container which is heated from the bottom. And heat transportation, so which is the topic under interest here, occurs partly by conduction of heat and partly by convection. So when the fluid moves and transports also heat. Okay, so what is observed is that for a small temperature gradient, so when you heat just mildly, the heat transfer is fully by conduction, while as the gradient increases, the configuration becomes unstable and there is a formation of convection cells. Okay, so typically this is the setting. So that's a picture from an experiment. So there's a fluid, which is some mineral oil. And then you put in some metal powder so you can observe the motion. It's not a pot where you want to cook your pasta. And you heat it from the bottom and then you observe this formation of convection cells. So typically the fluid goes like in circles and transports heat from the bottom to the top. So part is by conduction and partly by convection, by this motion. So, and what you observe is that as you keep increasing the heat from the bottom, the motion becomes more and more turbulent, and the convection component becomes more relevant compared to conduction. Okay, so here are the equations, and as a mathematician, I'm interested in all the constants set equal to 1, so but there will be one parameter. And I consider the problem with two approximations. So one is the Boussinesq approximation. So the dependence on density is neglected, except for the contribution of gravity. But the gravity involves the density, which in turn depends on the temperature. And I'm also interested in the infinite Prandtl number. So when the viscosity is much bigger than the thermal diffusion. Okay, so when you use these approximations and you couple the Navier-Stokes equation with the evolution of T, and then you're going to find the following system of equations. So here, the divergence of the velocity is 0 from the conservation law. Then there's a Navier-Stokes equation with the approximation and the diffusion and the convection of heat. Okay, so this happens in a domain which I consider to be a slab, a horizontal slab. So it's R2, and the height is h. So you heat from the bottom, and the top part has height h. So in the somehow increasing Rayleigh number limit, setting the constants equal to 1 forces the height h to be large. Okay, so this will happen in a large strip. And I will assume periodicity, horizontal periodicity of period h also in the horizontal variables. Okay, so you heat, say, a temperature 1 at the bottom, and at the top, the temperature is 0. So the heat passes from the bottom to the top of the container. Okay, so as I said, I consider, apart from the infinite Prandtl number, the limit in which the Rayleigh number is large. And this corresponds to having a very large horizontal strip. Okay, so the Nusselt number is the quantity which expresses somehow the heat transport by convection over that by conduction. So it's defined as the ratio between the total heat flux over the heat flux by conduction. So you would expect that when you heat up the fluid more and more, this would tend to infinity. Okay, so if W is the vertical velocity of the fluid, then from the previous equations, you're going to find the following equation for W here. So it solves a bi-Laplace equation, and the right-hand side is minus the horizontal Laplacian of the temperature. And you put both the Dirichlet and Neumann conditions at the boundary of the container, so top and bottom. And I need to introduce this notation. So if you have a function that depends on both space and time, f within brackets is the horizontal space-time average. So you take the average horizontally and also an average in time when the time goes to infinity. So it's a function which will depend only on the third variable because I'm averaging horizontally. Okay, here I'm cheating a bit, but okay, it's not a purely correct formula. It's a formula that say works. Okay, it's a honest cheating. There are some extra terms, but they are sort of harmless. So the Nusselt number can be computed in this way as the integral between 0 and 1 of the space-time average of theta and W. So theta is the temperature once you subtract the horizontal average. You can think of it as a sort of fluctuation of the temperature. And W is the solution of this problem. Okay, so the fluctuation, so since you have a maximum principle for the temperature, which runs between 1 at the bottom and 0 at the top, also this fluctuation theta is uniformly bounded. Okay, and so there was a prediction by some physicists, Marcus and Howard, in the 50s and 60s. So in the, say, mathematical notation, the Nusselt number, so this number here, should be bounded uniformly in h. So when h tends to plus infinity. Okay, so if you don't forget the physical constants, then somehow the upper bound you need is the following one. So the Nusselt number should be bounded by the Rayleigh number to the 1/3. Okay, and so there were results about this problem. So Constantin and Döring proved via a so-called background field method, which I might describe at the very end if I have time. So they proved the upper bound by the power 1/2, so which is a bit worse. But later papers by Döring, Otto, and Reznikov got an almost optimal result. So they got the optimal inequality up to a log of the Rayleigh number. And further on, so in 2018, Otto and Zeiss proved a better result. So they got the sharp bound up to a log of the Rayleigh number. And they combined somehow some estimates from the previous papers with the maximum principle of the temperature, which I said is always in the range 0, 1. Okay, and as we will see, so these logarithms, I'll try to give a glimpse of about the appearance of these logarithmic terms. They arise because you have to do with the integrals of the form 1 over x in the x. Okay, so which diverges logarithmically. But then you can try to get some more refined estimates from proper cancellations. Okay, and typically, I mean, one setting in which you find cancellation is the use of BMO functions. So I recall that the BMO norm is the sup over all cubes of the average integrals over the cubes of f minus the average in the cube, okay, which I denote by fq. And typically, a function which is bounded in BMO but not in an infinity is the logarithmic function. Okay, so for such functions, sometimes it's somehow natural to consider the BMO norms rather than the L infinity norms. Okay, and so result that we got this year is actually the upper bound with the, I mean, without any logs here. So mathematically is a Nusselt number just uniformly bounded or physically bounded by the 1/3 power of the Rayleigh number. Okay, so I'll try to give some idea. Okay, so I recall that theta is a sort of temperature fluctuation. And when you compute the horizontal Laplacian of the temperature, this coincides with the horizontal Laplacian of the fluctuation because you're subtracting only a function that depends only on the third variable. So the horizontal Laplacian doesn't see this, this term. And so we need to estimate an integral of this type. So I sort of threw a formula for the Nusselt number by means of this integral here. And I recall that W solves this problem. So it's a bi-Laplace equation in the strip with the Dirichlet and Neumann data on the top and the bottom. Okay, so what, you have a uniform bound on the temperature fluctuation theta, but the problem is that this is a kind of random function with values from the slab into -2, 2. Okay, so you need to prove bounds for theta with these constraints. So theta can, I mean, oscillate crazily. It's uniformly bounded, but you don't control at all the oscillations. And typically the problem is that when you solve, say, a Laplace equation with bounded right-hand side, it's not exactly the right functional setting to prove like Schauder estimates or so. All right, so here we're only interested in the range of x3 between 0 and 1. And we have as a domain a large slab. So as a first approximation, you can think of replacing the slab by the half space, x3 greater or equal to 0. And since you want to understand what happens near the bottom of the strip, well, then you can forget about what happens near at sort of very large height, roughly. Okay, in fact, the Green's function for the bi-Laplace operator in the half space is known since about a century, so from works by Boggio, and you can look at the rather recent book by Gazzola, Grunaut, and Swears. And here's the expression of the Green's kernel for the bi-Laplace with Dirichlet and Neumann data. So x is the pole, and y is the other variable. X star is the reflection of the pole x across the boundary of the half space. Okay, so typically you have appearance of these reflection points when you study electrostatics. So the typical method of the ghost charges when you want to understand the potential of the electric potential of a charge imposing like constant potential on the like on a plane then you need to add like a ghost charge on the other side. So this is kind of similar, just algebraically nastier. Okay, but that's the same idea. So you have an explicit form. And so thanks to this kernel, then if you forget about the upper boundary data here, so x3 equal to h, so if you pretend that you are solving in the half space, then the solution W to this problem will be given by the convolution of the Green's kernel, this kernel, with the horizontal Laplacian of theta. Okay? And if you integrate by parts, so if you pass the horizontal Laplacian here to G, you get a new kernel, which I call K, which is the horizontal Laplacian of G. All right, so you can derive an asymptotics for this new kernel K, which is the following. So with a good approximation, if you fix, so there is some scaling invariance, so and translation invariance, of course. So you can pretend that your pole is the point 0, 1. And you want to understand how this kernel behaves at infinity in Y. So it's a kernel, okay, if you forget about the explicit form, it's an inverse cubic at infinity. And there is, however, some improvement in the horizontal directions because there is the third variable squared here. So it's a inverse cubic in general, and there's a slightly better decay if you move to infinity horizontally. Okay, so when you want to use the representation formula, so when you integrate with this kernel, you can think of, so typically you divide your domain in cubes. If you move along the horizontal directions because of this faster decay, when you move horizontally, it's okay to integrate. It's also okay to integrate in cubes of this type, but the problematic cube is this one. So a cube which is of size h, so the height of the container, and which starts from height 1 to h. Okay, because here, so the volume form is r squared d theta, and then you have to integrate r squared versus r to the minus 3, and radially you get exactly the integral of 1 over r dr. And so if you split this cube into annuli, into dyadic annuli, then you get log h dyadic annuli. And therefore, if you just integrate that kernel versus a bounded function in a cube of this type, then you get a divergence of logarithmic type in the height h. So you want to be slightly more refined than this. And then we try to understand somehow more in detail the decay of this kernel at infinity. All right, so that's the asymptotics of the kernel, as I showed before. But it turns out that actually this kernel is reminiscent of a Poisson kernel. So it behaves like Y3 times the horizontal Laplacian of the Poisson kernel of the half space. Okay, so that's the Poisson kernel. And let me recall that the Poisson kernel gives you harmonic extensions to the half space of functions that are defined on the boundary. So you start from a function defined on R2, you convolute depending on the height S with the Poisson kernel, and that's the harmonic extension of your boundary datum. All right, so I need to introduce a so-called Carleson box. Sorry, did I start at 12:30? Sorry, 2:30. Okay. So I need the notion of Carleson box. So it's a box in the half space with comparable size and height. Okay, both are h, and I denote it by t x0 h. So there is actually some fundamental work by Pfefferman and Stein. So they proved that if you start with a boundary datum F and you take the harmonic extension, call it capital F, then this measure S, so which is the height times the gradient of the harmonic extension squared, is a so-called Carlson measure. So which means that when you measure with this measure a cube of this type, so which has volume h cube, because we are in 3 dimensions, actually the measure gives you h squared. And as a coefficient, you have the BMO norm of f squared, because it's quadratic in f. Okay, so if f is BMO, then you have this Carlson type estimate. All right, so how can you hope to use such a result? So our goal, because then I need to take a horizontal average, is that theta w, so this horizontal average, after I divide by, say, the size squared, horizontal, is of order big O of h squared. Okay, and I can assume by scaling reasons that the height is 1, so the one I'm interested in. And I'm sort of freezing the vertical variable in the temperature fluctuation theta. So I consider this as a function of y prime, the horizontal variable, depending on the height as a parameter. All right, so sorry, this is the slide with the most ugly formulas, and I promise there won't be any more. All right, so theta w is an average of this type. Okay, so I need to integrate horizontally. All right, but w is given by the convolution with theta. And so I have good terms, and the only bad term which I care about is the integral, is the convolution of the kernel over the bed cube. Okay, so that's the expression. And the hope, okay, what we tried was to make this formula more symmetric in theta somehow. So we passed one horizontal derivative here to this theta, and then we used the semigroup property of Poisson kernel. Okay, so we passed also a convolution by half of y3 on this side. Okay, so trying to make the formula sort of more symmetric in theta. Now the point is that here somehow, because we fix the height x3 equal to 1 here, so this sort of index that relates to the height is fixed, but this one is moving, so because we're integrating in S. Okay, so the point is that if this S was fixed, say equal to 1, as this one, then this would be exactly the Pfefferman-Stein estimate. Okay, because this guy here, if you replace S over 2 with S, would be exactly the harmonic extension of, say, theta 1 over, so from the horizontal space to the half space. Okay, and this would be exactly the Pfefferman-Stein estimate. Okay, and somehow we had to work to try to understand somehow, or to get similar estimates with the theta depending on the height here. And we exploited somehow some proof by Kaufman and Meyer, so in which they were able to exploit somehow some localization property in integrals of this form. So previously we had basically just one function in BMO, say bounded, okay? On the other hand, if you take another function which is more localized in L2, but fixed, they were able to prove a bilinear estimate of this kind. So here the function f and rho are fixed, and they use one BMO norm and one L2 norm, okay? So the proof uses, I mean, it's quite tricky, uses Fourier transforms in X, in the horizontal variables with a Littlewood-Paley decomposition. And so we were able to estimate, I mean, to extend this estimate to the case of a convolved term that depends on the height as well. And so we replaced the L2 norm squared in the right-hand side with the L2 norm of the so-called maximal function. Okay, so this maximal non-tangential function is the following. So when you have a function that is defined horizontally, but which might depend also on the third variable, well, you convolute with a Poisson kernel, take the gradient, multiply by S, and then you have a function which is defined on the half space, and you take the sup over a cone of this type. Okay, so when you replace the function rho here by this maximal function, so which is defined in R2, then you can actually extend such an estimate. All right, so I started making some approximation because the problem was set in a horizontal slab, but I passed to a half space. And somehow we need to fix the boundary data on the upper part. But that's, I mean, it takes some work, but it's not terrible. Okay, so suppose I call the W approximates the approximate solution. That depends on, this is an approximation for the vertical velocity. And so you need to add some sort of fixing term to get the correct boundary condition at the top. But somehow this correction will be biharmonic in the strip, and it will satisfy the correct boundary conditions. But because of biharmonicity, then you get a lot of regularity, say, near the top. So it's not so hard to prove estimates for this fixing term. Okay, so we use a Fourier decomposition, sort of ODE analysis vertically in the horizontal Fourier modes, and we can also control this approximate term. Okay, I conclude with some open problems. Okay, there is actually a paper in physics who did some numerics to understand the sharp bound, and they also gave a numerical constant. So it seems a very hard problem to understand somehow the best constant. And for this, we have absolutely no idea of how to proceed. Maybe, I mean, more doable, I don't know, maybe at least in some regimes. It could be the case of a finite Prandtl number. Okay, so I basically neglected because so the Prandtl number was infinite in the previous model. Somehow it's called the material derivative of the fluid. And so with the Prandtl number, it is there. So you get this, of course, more complicated equation. And there were, anyway, estimates for this model. Constantin and Döring proved that the Nusselt number was bounded still by the square root of the Rayleigh numbers for all the values of the Prandtl number. However, there is some work by a physicist, Spiegel. So he argued that if the Prandtl number is small, then you should improve on the multiplicative constant here. So somehow you should get some gain like the square root of the Prandtl number, the so-called implicit limits. And in a paper by Schofruth, Otto, and Nobili from 2016, so they were able to prove also some almost, we believe, sharp bounds on the Nusselt number in different regimes of the Prandtl number. And somehow beyond this range, the nearly optimal estimate coincides with the previous one. So it's a rather easy calculation. So there are no written conjectures, but we believe that possibly such bounds might hold without the logs also in this case. And I'm done. So I thank you for the attention, and I would like to wish a happy birthday to Anna Maria Ambieri.
So the scaling, I don't know the field. So the scaling is coming from dimensions, no, of the
yes, yes.
the 1/3. So it is valid both in the in the laminar regime and in the turbulent regime, or it is valid in, I mean, it is valid only in the turbulent regime, this type of scaling?
I think it's valid only in the turbulent regime.
Only in the turbulent?
Yes.
Okay, okay. So it goes beyond scaling. So it has some, I mean, it goes beyond the dimensional arguments.
Yes.
Okay.
I have to say I trusted somehow the physicist, but yes, it works for the turbulent regime. Yes.
The harmonic by polyharmonic operator. Is there a physical meaning or the
I don't know about
works?
the physical meaning. For sure, there would be. I mean, there are for sure estimates extending the ones by Pfefferman and Stein.
Mm-hmm.
They're not hard to prove in a sense because you might rely on these, and then by using elliptic regularity, you get the scaling for higher order derivatives of the biharmonic or polyharmonic extension. So I don't know about physical motivations for that, but certainly, I mean, scaling in varia estimates of this type would be there.
Okay, thank you. Okay, other question? No questions. So thank you again, Andrea. The second speaker of this session is Marco Degiovanni from Università Cattolica del Sacro Cuore di Brescia. He will speak about critical groups of functional associated with quasi-linear elliptic problems. Please.
Okay, thank you very much to the organizers for this invitation. It's a pleasure and also an emotion for me to be here where I started my academic career. I remember in particular the person that first I met, Antonio Marino, Anna Maria Micheletti, very benchi, my best wishes to them. And the topic concerns Morse theory and in particular in a particular setting, but first, let me recall some basic notions and results. We will consider Banach space and at the beginning function of class C1, standard notations for open sublevels, closed sublevels, the critical set level C. We have the usual concept of critical point, critical value, and Palismel condition at level C will appear in the global statements. The first part is the global Morse theory, because it is better to distinguish a global Morse theory, which is essentially a C1 theory without second derivatives, and a local Morse theory where second derivatives naturally appear. So further concepts, we will consider also formal series of powers with coefficient n bar and union plus infinity, with the sum in the usual way, also infinite sums, since the coefficients are non-negative, there is no problem in considering infinite sums, and the Cauchy product, as usual, with the convention that 0 times plus infinity is 0. In this way, all is correctly defined. And then, if we have two subsets of a Banach space, we will define the generalized Poincare polynomial, which is in fact a formal series of powers. In this way, there is a fixed field, K, and then one takes the dimension of the cohomology spaces as coefficients for the formal series of powers, and the cohomology is Alexander-Spanier cohomology, which is much more convenient in general. Then we will not display the field of coefficient K. And then the first basic result is a relation between global and local object, so-called Morse inequalities, which can be formulated in this way. First, we have to introduce a local concept. Namely, if C is a real number, we consider the critical set at level C, and we have three possible pairs. However, they have the same cohomology, or better, isomorphic cohomology. And then we can define the critical groups index of the critical set level C. For instance, in this way, we can take for critical groups the cohomology of the pair, and as index the Poincaré polynomial of the pair. These are local objects in this sense. They depend only on the value of the neighborhood KC, and of course, is if the critical set is empty, they are trivial. Then these are the ingredients, and with these ingredients, we can write the so-called Moss relation, Moss inequalities. For instance, in this way, we have a Banach space, a function of class C1, two values B could be also plus infinity, and we have the Palais-Zermelo condition. And I wish to stress that, first of all, A and B could be also critical. It is not necessary to ask that they are regular values. And also, F could have a lot of critical points. This is not a problem. In any case, there exists a formal series of powers which produces this equality. So at the right-hand side, we have the global object, in particular the generalized Poincaré polynomial of this pair of sublevels. And then on the left-hand side, several local objects. The sum of the index of all critical, the index of critical set level C. Now, since A, B are allowed to be critical, one has to be careful. If we take only the critical set with C strictly between A and B, then one has to take B open sublevel, A closed sublevel. The principle is that you have to consider the critical set in the difference between the sublevels. And so if you take open B, closed A, strictly between A and B. Also, you can consider also A included. In that case, both sublevels are to be taken open. And this is true in any case, even if AB are critical, even if you have a lot of critical points. So in particular, typical use of this kind of statement is that for some geometric reason, you know that the right-hand side, that polynomial Poincaré or Poincaré polynomial of the pair of strips contains some t to the power m. And since the coefficients are non-negative, then that t at the power m must appear also at the left-hand side. And so, since Kc produces 0, Kc empty produces 0, then it means that there exists C such that the index of some Kc must contain that t to the power m. So, first of all, some Kc is not empty. This is the first information. So far, it is just a matter of the formation lemma, and FC1 is enough. And this is the global part of Morse theory. Then there is the local part, which is the most difficult. In this case, the local part is most difficult than the global part. Namely, at a certain moment, you know that some Kc contains some term, and you want to deduce that there is really a critical point U with some more specific information. So at this point, we have to introduce something also for single point. Here it is a bit more complicated. So the point is that with respect to the previous situation, in general, if the whole critical set level C is substituted by a single critical point, in general, it is not true that we have isomorphism in cohomology. And then one has to introduce, in general, more objects. Specifically, if U is a critical point, we can introduce lower and upper critical groups in this way. For instance, open sublevel union the single critical point, open sublevel, or closed sublevel minus the single critical point. Both are meaningful. In general, they are different. In any case, they are local objects, as before. there is a most favorable situation if the critical point is isolated inside the case C, then there is the isomorphism in cohomology, then they are isomorphic, and then there is only one type of critical group. And also there is a simple situation in which it is easy to pass from the whole case C to single critical points in case C when case C is finite. Of course, in that case, they are all isolated, and then the critical groups of the critical set at level C is just the direct sum of the critical groups of the single critical points in the level, in the critical set. Okay? So far, these are general property. One could ask, and there is some hope to say which is the value of these critical groups. There is a first simple case, namely that of a quadratic form in Rn. And we take the 0, which is, of course, a critical point. Then this is the situation. If you take the lower critical groups, then you are described by the so-called Morse index, namely the supreme of the dimensions of the linear subspaces where the quadratic form is negative definite. In this way, the filter coefficient, if M is exactly the Morse index, otherwise 0. If you take the upper critical groups, then you are described as the large Morse index, which is the supreme of the dimension, but now quadratic form negative semi-definite instead of definite semi-definite. And this is the full description in the case of a quadratic form. And then one may hope, it is reasonable, that if you have a function of class C2, maybe the Hessian of the function will be the same job. This is true under some assumptions. First of all, this is natural. Suppose again we have Banach space, now a function of class C2, now the theory becomes of class C2, and we have a critical point, then the second derivative we can consider as a linear continuous map from the space to dual space, and we define Morse index, so the supreme of the dimension where the quadratic form is negative definite, and large Morse index where it is negative semi-definite, according to the previous description. And in general, this is the situation. It may happen that the Morse index is also plus infinity in general. This is possible. This is the general situation. Then there are most classical results in the setting of Hilbert spaces. In that case, there is a classical Morse lemma. Now there is a Hilbert space, and the second derivative is bijective. And then U is isolated, Morse large Morse index agree, and this is the description as in the case, similar to the case of the quadratic form. Here there is only one kind of a Morse index, and this is the description. Or to be precise, under these assumptions, it may happen that the Morse index is also plus infinity. And in that case, we are always in the second case, all critical groups are 0. This is possible. The assumption that the second derivative is bijective is quite restrictive. The function is said to be a Morse function if each critical point has this property, but there is a celebrated result by Marine Prodi, which says that if the second derivative at critical points is a Fredholm operator, which is a reasonable assumption, then it is possible to approximate the function in C2 by Morse functions, and then it's possible to use this Morse lemma in a reasonable way. There is also a result in the case in which is not bijective, the map is a result of Grommel and Meyer. Now the second derivative is just a Fredholm operator. Then it happens that now we have, in principle, a Morse index and a large Morse index. In any case, they are either both finite or both infinite. And we have this description, namely, the critical groups are trivial outside the closed interval between Morse index and large Morse index. which is also a useful information, because if you know that there exists a critical point with some critical group non-trivial, and you prove that some specific point has that group trivial, this means that there is another critical point. This is a typical technique to prove that there is another critical point, typically a non-trivial critical point. For a comparison between the two results, Morse lemma and the Gromov-Meyer result, it is convenient to observe a simple fact, and namely that actually the second derivative is bijective if and only if it is Fredholm and injective. So if you prefer, you can also say, in any case, Fredholm, and then injective, non-injective. Injective Morse lemma, non-injective, the general result of Gromov and Meyer. This is also a reformulation, which is also useful for subsequent development. This is the well-established theory in Hilbert spaces. Now, our interest in is Banach spaces. In Banach spaces, the situation is quite different, and there are also several open problems. First, simple remark. If you are in a Banach space and the second derivative is a Fredholm operator and the Morse index is finite, then the Banach space is Hilbertable. Namely, there is an equivalent norm which comes from the scalar product. And now it is well known that the Sobolev space, when P is different from 2, is not Hilbertable. This is a well-known result. So this means that if you are working in that Sobolev space and you imagine that the Morse index will be finite for compacted reasons, then it is impossible to have a Fredholm operator. Okay, so one has to think something different. Anyway, in a general Banach space for a general C2 function, there is at least one general result proved some years ago by Sergio Lancelotti. Namely, if you have a critical point, in any case, we have, with respect to the Gromov-Meyer result, half a result. Namely, the critical groups are 0 when B is less than the Morse index. And so the two problem is when M is greater than the large Morse index. This is the true problem, at least in the C2 setting in Banach spaces. There are no general results in this direction to my knowledge. And so for this reason, now we restrict ourselves to a more specific situation, that of functionals which comes from quasilinear elliptic equations. So now we skip to a concrete setting. We have a bounded open subset of Rn with a smooth boundary, a functional of this form. For sake of simplicity, we consider P less than n, but it is possible to consider P greater or equal than n. And the functional has this form. So essentially, the principal part includes two typical cases. K equals 0, which is the function related to the P Laplace operator. And K greater than 0, which is something like a P area functional, which is in some sense with the same behavior at infinity. The growth is the same, but regularized at the origin, because if K is greater than 0, then at the origin there is no degeneration, no singularity. On the contrary, with respect to the P Laplace operator. And also, in any case, there is a growth condition which ensures that the function is of class C1, and moreover, all critical points are quite regular, C1 alpha, omega bar. Since we are treating a local problem, we can allow also the critical growth. There is no problem with the critical growth at a local level. Okay, and then there are some results. First, consider the case P greater than 2 and also K greater than 2. Okay, so we add also an assumption to the similar term so that the functional becomes of class C2. Beyond class C2, we can define Morse index, large Morse index, as as previously. And then there are these results proved by Cingolani and Vannella. The first is like the Morse lemma, while the good assumption is that the second derivative is injective. You could remember that in the Hilbert setting, if one says, okay, the second derivative is Fredholm, then injective was injective, non-injective, a good assumption. Essentially here it is impossible to have a Fredholm operator, but there is enough compactness to do the job. And so in the end, injective, non-injective is a good assumption. In the injective case, it is like the Morse lemma, namely the critical point is isolated, the same Morse index, and the same kind of description. Otherwise, in general, there is the result like Grommel and Meyer. So all critical groups trivial outside the closed interval between Morse index and large Morse index. Second possibility, a bit more complicated, K is greater than 0, but P is between 1 and 2. And in that case, some non-smooth effect appears, because if P is between 1 and 2, then the functional, the principal part of the function in particular, is not of class C2, even if that function is extremely smooth. But there is a problem of smoothness in LP spaces, well known from the times of Krasnosielski, so that it is impossible to have a C2 functional. And so in this case, one have to give an alternative definition of a Morse index, large Morse index, which is possible in a quite natural way. Namely, about G, we can use this estimate, we consider this kind of estimate, which is in any case enough. And then the second derivative has to be substituted in this way. Essentially, one writes the concrete expression, the formal concrete expression. And instead of considering it on W1P, which is impossible, it is restricted to W120, where it is a very smooth, very good quadratic form. And then one defines Morse index, large Morse index, with this auxiliary Hilbert space. Of course, in this way, the space where we define the Morse index is different from the space where you have the natural functional. But in any case, it works, and we have essentially the same results we prove with Cingolani and Vannella, namely, if that quadratic form, that operator actually is injective, then the point is isolated, we have the description like the Morse lemma, and otherwise, we have the results like, say, Grommel and Meyer. In this case, also the case M less of the Morse index is new because the function is not C2, so cannot be deduced from the general previous result. And now I want to spend some words on the case K equals 0. K equals 0 is the pure P-Laplacian in the operator. So the function has this form. I want to remember that the radial case has been already treated by Aftalio and Pacella, and so now we are interested more specifically in the case P is greater than 2 and omega is general. There is no particular symmetry. Since P is greater than 2, we can still consider a C2 setting. So with good estimate on the semilinear term, we have a function of class C2, and so when the M is less than the Morse index, the result of Lancelotti applies, and we have that result. So we are interested in the large value of M, when M is greater than some large Morse index. Here the problem is also the definition of large Morse index, because in this case it is not so obvious. To understand it, let's see a moment the situation when K was greater than 0, which is the simpler case. So when P was between 1 and 2, we had to consider this quadratic form because the function is also C2. And when P was greater than 2, we had two possibilities to consider the second derivative, the Hessian, in the natural space W1 P0, or the same quadratic form, which is meaningful also when P is greater than 2. This is not a problem because of regularity results, one gets the same indices. Why? Because in principle, what is the problem of the large Morse index? Since we take the space where the quadratic form is negatively semi-definite, in particular consider also the kernel where it is 0. And why? Which is the irregularity? If you are considering the first possibility, you are considering the elements of the kernel, we are in W1P0. If you are in the second case, the elements of the kernel, namely the U, which satisfies a suitable elliptic equation, but in W120. Now, the point is that here there are regularity theorems which ensure that if you are in the second case, automatically you are with the W1P0 regularity, and so there is no problem. But if you are considering the case k equals 0, there is a problem with the smoothness. And so it's not so obvious which is the regularity of the element of the kernel. And so there is the risk to underestimate the dimension of the kernel. And so to produce an M star which is below the true level, the correct level, the correct value. So at this point, we have to consider an auxiliary Hilbert space, which depends in general on U. First of all, this is the second derivative of the functional, looking particularly at the principal part. Okay. Actually, the first term of the principal part is the leading term. Okay. And then having in mind this expression, we consider a space in this way. In general, if U is 1 omega bar, we introduce the space of V's in W110 intersection L2 such that, say, the main contribution is finite. Okay? So it is better to consider W110, so large space. Sometimes the integral will be plus infinite, sometimes it will be finite. We consider where it is finite. Okay? And then this is a linear subspace. If you add the L2 contribution, that W squared, this is a norm, in any case, which comes from a scalar product. We can consider the completion, which is, of course, a Hilbert space, which is intermediate in general between W120 and L2. In principle, we could apply also this to the previous case, and then one get W120 simply. Here, since there is a degeneration, because where the gradient of U vanishes, the principal part degenerates, this is something intermediates. And then this expression allows to produce a relaxed form, a relaxed expression of the Hessian, because here you have the two main contribution of the second derivative in a relaxed form, because there is a completion, plus an L2 norm. And then we can produce the Morse index in this way. First, we define the variational eigenvalues, say, with respect to the L2 norm. This is not essential. So the numerator is that norm, which was only the principal part plus L2 norm. And so now we, -1, we subtract the L2 norm and we add the contribution of the semilinear term. And then this is the usual infamax, which is well known as variational characterization of eigenvalues for quadratic forms. It is also convenient to say that lambda 0 is minus infinity. And then we produce a new large Morse index, which is the supremo of the number. We see the say naive in a naive set the number of eigenvalues which are less or equal than 0, which is also what one could imagine, but after a technique of relaxation and so on. And then this will be the reference. The situation is the following. In particular, since we have enlarged the space, the eigenvalues are below, and so the large Morse index is greater in principle, because we have below eigenvalues, and so the eigenvalues have decreased, and so the large Morse index has increased in principle. Okay, now this is there is need also the fact that this auxiliary Hilbert space is well behaved. Coming back to the case k greater than 0, in that case, a fact, which is not an assumption, is a fact important, is that W1 to 0 is weakly compact in W1 0, ovviamente, in weak W1 to 0 and strongly precompact in L2, and this is a fact. Now this becomes an assumption, namely, essentially, we have to require that that Hilbert space is weakly precompact, say in W110, this is enough, and strongly precompact in L2. So this becomes essentially a problem of a regularity theory, because you have a degenerate operator, a degenerate quadratic form, and the regularity of this embedding, which depends on regularity properties. And this is a subject already studied, in particular by Damascelli and Schunzi. And here we need something similar in a uniform way. More precisely, we consider, instead of f, a family of functionals, f epsilon, for epsilon equal to 0, this is exactly our functional. Otherwise, there is a regularization by this further term. And then this is the condition. We say that at critical point, we have a precompacted condition if we have something like the previous proposition concerning the precompactness in weak W11 and strong L2, but also we consider a converging sequence of critical points. Each UN is a critical point of some f epsilon n, with epsilon going to 0. So a uniformized version of the previous property. And then we have the result with the Cingolani and Schunzi. The general result is that if at a critical point you have this condition, then that new large Morse index is finite, and we have the result we may imagine. And of course, at that point, one could ask, and there is some hope that the precompacted condition is satisfied. And the answer is yes. For instance, in this case, if we have a nonlinearity of typical type, namely less than 0 when the argument is s is greater than 0 and otherwise 0, which is quite a typical situation, then this condition is satisfied. And then we have also the consequence given by the previous result. So at least in this case, we have a complete result. This is not only the other case, the only case, I have no time here, but this result can be applied also to sign changing nonlinearities in the radial case, for instance. So also in the radial case, there is some improvement. But the main object was to consider non-radial situation without any particular symmetry. So I thank you for the attention.
I have a question which is maybe completely stupid, but you know, we're among friends, so I'll make it anyway. So for the case of P between 1 and 2, when you said somehow in the natural space, the function is not of class C2, if I understood correctly, would it make sense to consider, I mean, not maybe a second derivative, but some like 1 plus alpha derivative? I don't know exactly what I'm talking about, but I was wondering whether it would be a way to approximate maybe a functional by something which is maybe less than linear.
I don't know. Also, I don't know if it is useful, because the point is that if we consider the case P between 1 and 2, okay, this is not C2, but we have this concrete expression, which is a good expression in the space W1 to 0, okay? Because since k is greater than 0, then we have the non-degeneration and non-singularity in the origin. So in the end, you can hope to estimate the eigenvalues and the Morse index of Q. Okay, so it's not C2, but in the end, one produces a concrete object whose eigenvalues and Morse index maybe can be calculated. If you introduce a strange derivative, is it possible then to say something? The true problem is in some sense the next step. It is possible to manage it because in the end, it was smooth, but the quadratic form is a good expression. It's not a bad quadratic form. So
I'm asking because I've seen results in regularity theory in which it was not allowed to somehow differentiate the equation, but formally it was okay to take a half derivative. So I was wondering whether, so this was just in regular space in n variables. So I was wondering whether maybe...
Here, in some sense, we are in a different direction, which in some sense goes back to my thesis. So that was operators in the presence of more spaces. And also here we are in presence of more spaces. There is a natural space 1P, W1P, where you have the natural functional and the Palais-Mail condition. And another space which is good for the Hessian. So this is the situation.
Okay, thanks.
Io, prima ancora di ringraziare vivamente e calorosamente gli organizzatori e fare gli auguri più caldi ad Anna Maria e a Vieri, ma prima devo scusarmi per 3 cose. Primo, del ritardo con il quale sono arrivato. Non è dipeso da me, però. In secondo luogo, perché parlo italiano, per un motivo semplice, che non ci ho pensato e ora non sono viceversa così padrone dell'inglese da farlo immediatamente. E terzo, perché non parlerò di matematica. Forse quest'ultima cosa non vi dispiace o forse vi rallegra. Questo, grazie. Conosco Anna Maria e Vieri da molti anni e la circostanza che ci trovassimo insieme nella stessa sede universitaria e avessimo in comune gran parte dei nostri interessi scientifici ci ha permesso di frequentarci molto e di scambiare tante riflessioni e tante idee. Sia con lei che con lui abbiamo parlato spesso di matematica, ma ricordo volentieri le numerose chiacchierate piacevoli e interessanti, con Vieri qualche volta tumultuose, che ci è capitato di scambiare su tanti altri argomenti della cultura e della politica. Insomma, anche in questa bella circostanza risalta il fatto che uno degli aspetti più belli e interessanti del nostro lavoro è offerto da quel tessuto di relazioni scientifiche e umane che gli studiosi riescono a stabilire fra loro, specialmente quando si scoprono appassionati per uno stesso specifico ambito di ricerca. Aggiungo ora con molto piacere che questa ricchezza di relazione intellettuale umana è effettivamente una delle caratteristiche più evidenti dell'ambiente di studio che sia Anna Maria che Vieri hanno saputo creare attorno a loro. Delle loro belle ricerche scientifiche ho già avuto modo di fare qualche piccolo cenno in altre occasioni. Del resto, da alcuni anni mi è mancata l'occasione di seguirne gli sviluppi. Con Anna Maria ho anche potuto collaborare in diverse occasioni a ricerche comuni e ricordo qui con particolare piacere il lavoro assiduo che lei ed io facemmo insieme a una giovanissima Mariangela Pistoia che non c'è. Dov'è? Dove sei? L'ho persa. E allora dottoranda riguardo a una ricerca interessante e impegnativa. Ricordo che Mariangela in seguito lasciò capire, fra il serio e lo scherzoso, che il lavoro fu così intenso e pressante che quando alla fine Anna Maria, lei ed io potemmo tirare le fila, fu per lei un vero sollievo. Ma in questo convegno voglio aggiungere che la cordiale apertura di rapporti è uno dei tratti principali di tutto l'ambiente degli studiosi italiani e stranieri che sono qui oggi in qualche modo rappresentati. C'è un comune interesse scientifico che, anche per merito di Anna Maria e Vieri, ha propiziato una più ampia relazione culturale e umana, che qui è evidente. Del resto, come accade nella ricerca scientifica e nella stessa vita, su questo ambiente hanno influito in qualche modo, diretto o indiretto, anche altri studiosi, fra i quali in particolare Giovanni Prodi e anche Ennio De Giorgi. Ma oggi qui è assolutamente doveroso e anche gratificante rivolgere a Prodi il nostro ricordo. Soprattutto verso di lui i cultori italiani di analisi non lineare sono fortemente debitori. Sono sicuro che tutti i presenti sono ben lieti di ricordare che questo è l'ambiente che si è costituito intorno al filone di ricerche scientifiche sostanzialmente introdotto in Italia da Giovanni Prodi fino dagli anni 50 del Novecento e da lui promosso con valore e lungimiranza scientifica. Prodi seppe avvertire il vento nuovo che spirava negli ambienti della ricerca matematica europea della prima metà del secolo e seppe entrare in quella corrente allora impetuosa con un'apertura e un entusiasmo dei quali tutti oggi dobbiamo essergli grati. Per dare un'idea di quanto quegli studi fossero percepiti in Italia come un'importante novità, posso per esempio ricordare un'osservazione di Aldo Andreotti, il grande e famoso professore di geometria che coltivava amplissimi interessi scientifici ed era particolarmente sensibile proprio all'analisi matematica. Una volta, credo fossimo ancora verso la fine degli anni 60, io ero da poco laureato, Andreotti era presente a una relazione di Prodi in uno di quei seminari che, secondo una bellissima abitudine di quel periodo, venivano organizzati quasi ogni mese fra studiosi di materie diverse, come analisi, c'erano Prodi, Stampacchia e De Giorgi, algebra, c'era Barsotti, geometria, c'era Andreotti. Al termine dell'incontro, dunque, Andreotti ebbe a dire più o meno: dobbiamo prendere atto che sono di nuovo gli analisti a gettare il sasso più lontano. Del resto, anche Prodi era aperto verso un orizzonte scientifico senza limiti a priori. Noi giovani conoscevamo bene l'ampiezza, giovani allora intendo, l'ampiezza dei suoi interessi. La sua era un'apertura scientifica che lo rendeva curioso di ogni novità. Devo dire che a me, nei primi anni dopo la laurea, quegli spunti in tante direzioni creavano una certa difficoltà. Di quel vento nuovo, dunque, Prodi seppe far giungere fresche folate anche in Italia, portando un vero rinnovamento nella ricerca matematica, soprattutto in analisi, di quegli anni. Con l'occasione possiamo però ricordare che questo filone di ricerche aveva già avuto un primo inizio in Italia una decina d'anni prima, con Renato Cacciopoli e Carlo Miranda. In Italia quelli di Cacciopoli e Miranda furono davvero studi pionieristici, i quali però sembra che per alcuni anni non ebbero seguito. Forse la difficoltà veniva proprio dalla netta discontinuità che essi introducevano nell'ambiente della ricerca matematica italiana. Ma come sappiamo, questi studi in Europa si erano sviluppati già da molti anni, soprattutto nell'Europa centro-orientale, anche se alcune radici profonde le possiamo trovare anche prima, soprattutto per limitarsi a un'epoca recente, relativamente recente, in Henri Poincaré, che ha lavorato nell'Ottocento, per lo più. Vedo inoltre che Lusternik ricevette il premio Stalin già nel 1946, dunque i suoi studi e la sua scuola erano già iniziati ben prima di quell'anno. Guardando alle origini di questo tipo di studi, nella situazione dell'Europa di oggi, riunita in una comunità di stati e di popoli ispirati da una grande idea comune, e tuttavia teatro di guerre e di tragedie, e affetta da piccoli nazionalismi e piccoli egoismi, avvertiamo subito la necessità di ricordare un fatto culturale di grandissimo rilievo, un fatto ben noto che è davvero urgente riportare oggi al centro dell'attenzione, e cioè la essenziale unità cui era pervenuta fino dall'antichità la cultura europea. Una cultura che, come ben sappiamo, ha introdotto semi di umanesimo e di scienza nella storia di tutto il mondo. Non è questo certo il momento di soffermarsi, nemmeno per poco, su quella unità di percorsi e di traguardi che nei millenni, superando guerre, fanatismi, errori e orrori, si è comunque realizzata in Europa e nel Mediterraneo. Ma anche se ci limitiamo a queste nostre materie specialistiche e anche se restringiamo lo sguardo a epoche relativamente recenti, quella unità balza agli occhi, o meglio ci appare così naturale che quasi non le prestiamo attenzione. Qui ci basta ricordare alcuni dei nomi a noi più familiari fra i matematici che troviamo alle origini degli studi, per così dire, non lineari. Abbiamo prima accennato a Poincaré, che era francese e ha trascorso gran parte della sua vita nell'Ottocento, mentre Lusternik ha operato interamente nel Novecento. Lusternik era un ebreo polacco, come Ulam. Polacco era anche Borsuk, mentre Schnirelman era ebreo ed era nato a Mosca. Brauer era olandese e Krasnoselski era ucraino. Krasnoselski già nel 1956 aveva pubblicato a Mosca il suo bellissimo libro sui metodi topologici nella teoria delle equazioni integrali non lineari, che poco fa qualcuno ha e che Marco ha ricordato. Ma questi accenni sulla irrilevanza rispetto al mondo della cultura e in particolare della scienza di certe malintese barriere nazionali e religiose, desidero richiamare due magnifici nomi della matematica mondiale che sono venuti a mancare in questi anni, persone che molti dei presenti hanno potuto frequentare e ammirare. Li cito perché la loro formazione culturale era diversa dalla mia, non erano italiani, e anch'essi, come molti altri, sono la dimostrazione del fatto che valore scientifico, alto livello umano, origini culturali diverse e propensione all'incontro aperto e cordiale sono fattori fondamentali, propulsivi della ricchezza degli orizzonti di valore e di pensiero che si offrono all'umanità. Il primo nome che desidero fare è quello di Abbas Bari, che era tunisino, era arabo ed era musulmano, anche se da anni aveva in Italia. Abbas era di ben 16 anni più giovane di me ed era giovanissimo, o almeno giovane, non ricordo bene la sua età, quando è morto nel 2016. L'altro nome è quello di Haïm Brezis, che era ebreo ed era nato in Francia. Anche lui di qualche anno più giovane di me, è mancato poche settimane fa, all'inizio dello scorso luglio. Abbas e Haïm erano entrambi bravissimi matematici, erano entrambi dotati di amplissimi interessi scientifici e umani. Con loro ho potuto intrecciare scambi di idee e di vedute su tanti problemi, anche del tutto diversi dalla matematica. Posso testimoniare anch'io, come credo molti di voi, che essi erano affezionati al patrimonio culturale delle loro origini ed erano anche accomunati dalla visione di valori che appartengono a tutta l'umanità. Quella visione comune, quell'apertura al confronto, erano evidentemente ritenuti in piena armonia con ciò che essi consideravano il patrimonio di pensiero, usi e tradizioni ereditato dalla comunità di origine e custodito con cura attraverso la riflessione e la rielaborazione personale. A proposito di riflessione critica, siamo noi i primi, noi italiani e noi europei, siamo noi che dobbiamo proporci di ripensare alla involuzione di una certa cultura di basso livello, aggressiva e superficiale che si sta diffondendo in Europa. Si tratta di una cultura pregna di parole ostili e di individualismo, diffusa nel dibattito che si pretende politico o sociale, una cultura che afferma molti diritti dell'individuo e non li confronta con la responsabilità che ognuno di noi ha verso la comunità umana. Parlo dell'Italia e parlo dell'Europa di oggi. È una indisponibilità al confronto che sembra gradita a tanti, mentre insidia sempre di più l'eredità del grande incontro che nelle scienze e nell'umanesimo è stato costruito nella storia dell'Europa e del Mediterraneo. Un incontro che ha generato ricchezza di pensiero e che ha saputo superare ogni confine di paese e di continente. Di quella ricchezza siamo debitori a tanti grandi personaggi della storia del mondo antica e moderna. Dobbiamo a persone di grandi ideali se dopo la Seconda Guerra Mondiale è nata felicemente la comunità europea, che ora incontra tante difficoltà. Lasciatemi fare solo un attimo solo i nomi, di Konrad Adenauer, Alcide De Gasperi, Robert Schuman, Jean Monnet e Altiero Spinelli. Li ho citati in ordine di nascita. Siamo debitori al coraggio con il quale loro e tanti altri hanno saputo reagire all'oppressione culturale e materiale delle dittature. Oppressione culturale e materiale. E hanno affrontato carcere e persecuzioni. Non possiamo certo farlo ora, ma dovremmo riflettere attentamente sulle derive culturali europee di allora e di oggi. Ma un esempio desidero farlo. È un esempio che per noi europei è particolarmente mortificante. Penso, non so se la penso io così, penso a tutta la vicenda di Charlie Hebdo. Abbiamo assistito alle offese vergognose e volgari che un settimanale satirico francese ha inferto per settimane a ciò che i musulmani hanno di più caro e di più sacro, alla barbarie degli omicidi con i quali dei fanatici assassini, meno abili con la penna, ma più esperti con il mitra, hanno sfogato il loro rancore, e infine al mortificante spettacolo offerto da governi di tutta Europa, convocati a Parigi per riaffermare che la loro libertà di espressione comprende il diritto di recare le offese peggiori a chi professa fedi o convinzioni sbagliate. Quanto alla responsabilità che ognuno di noi ha in tutto ciò che dice e che fa, nei confronti di chiunque altro e verso tutta l'umanità, in quella solenne riunione non ne appariva traccia. E non è mancato chi quegli insulti e quegli omicidi li ha giustificati. Del resto, noi europei progrediti abbiamo avuto in Italia e in tutta Europa dei fanatici svelti con la parola quanto con il mitra. Ne mancano gli indizi che di tali persone ce ne siano ancora, mentre di parole pericolose, piene di aggressività e povere di idee vere, ne sentiamo tante, anche da personaggi in vista. Insomma, anche questa volta sento la necessità di concludere dicendo che tutti noi, nel mondo che ora che pretende di essere il mondo della cultura, abbiamo delle responsabilità che non possiamo ignorare. Abbiamo il compito di promuovere come possiamo la riflessione seria sui problemi di oggi e di invitare a un confronto politico e sociale volto a capire e a capirsi fra persone che partono da prospettive, culture o intuizioni diverse. È questo, lasciatemi dire, un necessario esercizio di intelligenza del quale appunto siamo responsabili. Con questo rinnovato invito rivolto a tutto il nostro mondo dello studio e della ricerca a far fronte alla responsabilità di promuovere una reciproca intelligenza, ringrazio di cuore Anna Maria e Vieri per la loro opera e per l'ambiente scientifico e umano che, come ripeto, hanno saputo costruire intorno a loro. E rivolgo a entrambi gli auguri più calorosi.
Okay, so I change a hat, and as a director of the Giorgi Center, I would like to just say a few words about Centro De Giorgi. Of course, I'm just making a standard speech, so my speech cannot compare, of course, to Antonio's. But, okay, I will be very quick. So the George Center was founded about 20 years ago, formally as a research laboratory of Scuola Normale, but with the goal of being, of creating opportunities for the mathematical community of Pisa and its visitors to gather. It's funded mainly by Scuola Normale. We have a very big contribution from the University of Pisa, and also there is some funding from Scuola Sant'Anna. And in fact, especially at the University of Pisa, so we have a main source of mathematicians. So the main activities of the center since the foundation have been workshops, schools, intensive research periods. And recently we also started the colloquium series. We have visiting positions of two types. So there are opportunities to perform research in pairs or in groups for short periods, typically. And we have postdoctoral positions of the duration of 2 years. So typically the opening is in the fall with a deadline in early January. And that's all I wanted to say. So I would like to thank the organizers for bringing up this really high quality event, and also the staff of the center who is not here for the constant and valuable support. Thank you.
Before to make start this second part of this afternoon, let me just say a couple of words. The first one, for people who is younger than we are, why Pisa and Bari together for this occasion? Because in the past, there was not a PhD course in Bari, and there was a strong connection between Pisa and Bari thanks to Dino Fortunato and Vieri Benci and Antonio Ambrosetti, who sent a lot of students who took their degree in Bari to study in Pisa for the PhD, or at Scuola Normale with Antonio Ambrosetti, or at university, and with Vieri and Antonio Ambrosetti. So a big group of nonlinear analysis and variational methods worked, starting their research in Pisa. This connection is why we were ready to join to the co-authors who are still working in Pisa in order to organize this meeting together. The second thing I want to point out is that this year is the 30th birthday of the splitting lemma that Vieri Benci and Dino Fortunato wrote as publication, because they wrote it before, for studying geodesics in variational, in semi-Riemannian manifolds. And as Antonio knows very well, he was there from the beginning about this story of a piece of research in nonlinear analysis. And for what is about me, I took my PhD in Pisa, and some of the first people I was able to meet was Vieri and Anna Maria when I arrived here in 90. So there are a lot of years that I was able to know them. And I like the idea that there are new generation coming to Pisa to study variational methods and to have, in some sense, an heritage which is joined between Bari and Pisa, and not only because, as good friends know, there is Bernard, there is Marco. There was a very nice group built in around topological methods, which involved many universities and more cities. So it's a pleasure for me to be here as a co-organizer, and I want to thank all the other co-organizers, Marco in special, because he was the one who took care of all the mails in our behalf. And I want to thank the Georgi Center and its staff, because they helped us a lot. Since it's not the first conference I organized, but it is the first time I have a staff who is able to take care of all the details, when usually it was something crazy you have to add to the classical professional life. So it's a pleasure for me to introduce the first speaker of this second part of the conference, and it's Paolo Mancosu. I ask forgiveness, from Berkeley. from Berkeley. He will talk about a free application of Zermelo's theorem on part whole.
Thank you very much. Good afternoon, everyone. I would like to thank the organizers for this kind invitation, which strengthens my ties to Pisa. So the talk is about 3 applications of Zermelo's theorem on part whole. The overview is I'm going to give you, first of all, a statement of Zermelo's theorem on part whole. It's not usually known by this name. And then I will successively go into the different areas. So this is a foundational talk that brings together issues in philosophy of mathematics and probability theory with technical results in logic. So the second part will be on neologicism and inconsistent abstraction principles. And there is a section on the axiom of choice in second-order logic. And finally, one part on probability theory on the notion of regularity. So as I said, the aim of the talk is to give you a brief overview of this result by Zermelo to 3 very different areas of investigation. I will draw upon 3 articles which I published recently with different collaborators. Given the time constraints, I will give no proofs of any of the results, which anyway are contained in the articles. I care more that you get a sense of what the general outline of the investigations look like. So here are the 3 articles I'm referring to. The first one was published in 2019, and is the one that contains the key results on neologicist foundations and inconsistent abstraction principles and how that relates to part whole issues. Then there is a paper published with Siskind and Shapiro in the Review of Symbolic Logic on the axiom of choice in second-order logic, or choice principles, I should say, in second-order logic. And finally, an article that just came out in Philosophy of Science with Guillaume Massat, who is in fact a postdoc at the Normale in Pisa right now, on totality, regularity, and cardinality in probability theory. Now, what is common to all these 3 articles is the exploitation of a theorem by Ernst Zermelo to situations in which the relation of strict subset inclusion, which I call part whole, with, of course, a reference to quite a bit of work that has been done in that, using part whole relations in that sense, is of relevance. Now, the theorem in its set-theoretic version is implicit in Zermelo's very famous article of 1904 on the equivalence between the axiom of choice and the well-ordering principle, but it was brought out explicitly in an article by Kanamori in 1997. It's a beautiful statement just because of the simplicity and the range of applications to which can be put. So here it is. Take an arbitrary set, X, and an arbitrary function that sends you from the full power set of X into X. Then there are sets A and B in the power set such that A is strictly included in B, but the function F identifies their values. So the theorem can be proved using transfinite induction without using the axiom of choice. So by a failure of part whole, in general, I will mean the fact that a function, such as that discussed in Zermelo's theorem, fails to keep track of the strict subset inclusion between some sets A and B, yielding therefore f of A equals f of B, despite the fact that A is strictly included in B. So first, the application to neologicism. Now, neologicism emerges in the contemporary debates in philosophy of mathematics with Crispin Wright's book called Frege's Conceptions of Numbers as Objects from 1983. Wright's project was to show the viability of a philosophy of mathematics that could preserve the key tenets of Frege's approach. Now, prima facie, this could have appeared as an impossible task. After all, Frege's foundational system, as first presented in the Foundations of Arithmetic, and then in final formulation in the Basic Laws of Arithmetic, relied on the use of extensions, which were codified by means of the notorious Basic Law 5 in the latter work, a law that was shown by Russell to lead to contradiction, right? This was the essence of Russell's paradox. Now, basic law 5 postulates the existence of a function epsilon that maps the concepts into the objects of the domain in such a way as to satisfy the following statement. For every concept x and y, the extension of x equals the extension of y if and only if x and y are in fact coextensional. The same objects fall under both concepts. Now, I know there are many of you who are not so familiar with this talk about concepts. So every time you hear concept, if that gives you problems, think of it as a subset of the domain, because we're talking anyway about monadic concepts, and they are interpreted as extension, as being subsets of the domain. So in this particular case, what we have is just basically a form of extensionality. The function assigns an object to the sets and assigns the same object if in fact, the sets are equiextensional. It is easy to show that basic law 5 yields an unrestricted comprehension axiom, which in turn yields the existence of Russell's paradoxical set. Frege himself and a few after him tried to tweak basic law 5, but with no success. And until Wright's book, Frege's foundational project, i.e. logicism, was no longer considered viable. Wright's approach emerged from a combination, or as a powerful combination, of a technical result and a host of philosophical arguments. The technical result was motivated by the observation that in the foundations of arithmetic, Frege used extensions only in order to prove what is now called Hume's principle. This is another principle, which is called an abstraction principle. So here, the principle says that for any two concepts, x and y, but again, you can think of them as sets, the number of the x equals the number of the y if and only if x and y are in one-to-one correspondence, or the objects that fall under x and y are in one-to-one correspondence. Now, this is just basically Cantor's criterion of identity for sizes, for cardinality. Hume's principle then states exactly this idea that the number of associated to a concept equals the number associated to another concept if the objects that fall under those concepts are in one-to-one correspondence. Now, what Wright showed was that once Hume's principle was established, Frege did not have any further use or extensions and proceeded in the foundations of arithmetic to provide an outline of how to prove from Hume's principle and second-order logic the basic axioms for second-order arithmetic. So the technical result then was Wright's detailed reconstruction of how to derive, within second-order logic, the basic axioms of second-order arithmetic from Hume's principle, and of course, definitions, which you need to define zero, successor, and so on. Now, if we call FA for Frege arithmetic the system of second-order logic containing Hume's principle, and with PA2 the usual axiomatization for piano arithmetic second order, then Wright's result can be summarized as follows: that from Frege arithmetic, you can infer in pure second-order logic the axioms of second-order arithmetic. So this discussion has led to a detailed scrutiny of abstraction principles, of which BL5, Basic Law 5, and Hume's principle are the two most famous instances. Indeed, one of the first objections to accepting Hume's principle as a starting point was an argument, which is the first form of a bad company objection, which questions the legitimacy of using definitions such as Hume's principle, arguing that something fishy must be going on here, as shown by the fact that Basic Law 5 has exactly the same definitional form as Hume's principle, but gives rise to a contradiction. So how can we be certain or safe with assuming Hume's principle? And this led to the first requirement of a long series to come for separating good from bad abstraction principles, namely consistent. it was easy to show that Hume's principle was equiconsistent with second-order piano arithmetic. And since very few people have doubts about the consistency of second-order piano arithmetic, that gave the first criterion for, as it were, eliminating basic law 5 as a bad principle. However, if we restrict our attention to operators from monadic concepts to objects, such as BL5 and HP, well, basic law 5 was, until the appearance of our work on the subject, the only example of an operator giving rise to inconsistency, thereby making it appear as a sort of monster in an otherwise regular universe of abstraction principles free from this pathology. The use of Zermelo's theorem here is crucial for showing that basic law 5 is only an instance of an infinite class of inconsistent abstraction principles. And by doing this, I give a massive generalization of Russell's paradoxical result. In fact, so what do abstraction principles do? Well, in the Fregean context, they compress the concepts into the domain of objects according to an equivalence relation on concepts. When one looks at the situation set theoretically, this corresponds to the idea of mapping the power set of a set X into the set X itself according to an equivalence relation defined among the elements of the power set. In the case of BL5, basic law 5, this relation is the extensional identity of the sets. In the case of Hume's principle, is the existence of a one-to-one mapping between the sets. So in a Fregean setting, an abstraction operator is an operator on concepts, delta, such that the delta of X equals the delta of Y, if and only if X E Y, where E is some equivalence relation of concepts. Now, what would it mean to say that delta must satisfy a part-whole constraint? Well, we say that an abstraction operator satisfies part-whole if the following condition holds, that for every concepts or sets, if you want, if X is strictly included in Y, then delta keeps track of that very fact. Okay, then delta X will be different from delta Y. Now, of course, this relation fails for the number of operator. We very well know that the set of even numbers and the set of natural numbers, because they are in one-to-one correspondence, will get the same value. So that particular operator doesn't keep track of part-whole, but basic law 5 does. In fact, it is defined exactly in such a way as to keep track of extensional difference. So, but part-whole, as the principle I just gave, has no standard model in a Fregean setting, i.e. a model in the form of a domain X, the full power set of X, and a function from the power set into X, where the power set is the full power set. Why? Well, because Zermelo's theorem shows that for any set X and for any F, if F sends the entire power set of X into X, then there must be sets A and B such that A is included in B, and, well, in this case, what I need is F. F of A equals F of B, showing that the abstraction operator cannot keep track of that strict subset inclusion. Since Frege systems are second-order systems, though, this unsatisfiability does not automatically lead to a deductive refutation. And this is on account of Gödel's incompleteness theorem, because in second-order logic, the fact that we don't have models in this way is not tantamount to having a formal contradictory theory. However, and this is what we do in Mancosu and Siski in 2019, we can show that second-order logic can deductively refute the existence of any such operator. The technical details are complex, as one needs to show that second-order logic has the resources to bypass the appeal to transfinite induction that is used in the standard proof for Zermelo's theorem. You have very little set theory in second-order logic. But the formal result can be stated as follows. take the turnstile to denote provability in second-order logic, just with the usual natural deduction rules, plus substitution rules for first and second-order terms and the usual axioms. Then we define the following sentence in the expanded language. So we have second-order logic plus an extra symbol for a function delta. Now, part whole is the sentence that says for all x and y, if x is strictly included in y, then delta keeps track of that by giving them different values. So part whole says that delta respects part whole. Well, as I said, there are abstraction principles which deductively imply part whole. For example, basic law 5. So the following theorem gives a new proof of the inconsistency of BL5 and the first proof of the inconsistency of any other abstraction principle that deductively implies part whole. Theorem 2.1, in second-order logic, just with the addition of a function delta, we can refute formally part whole, the statement part whole for the function delta. The details of the proof are not needed to understand the main consequence of the result. The basic formal inconsistency, i.e. the deductive refutability of basic law 5, can be seen in the context of a wider family of formally inconsistent abstraction principle, i.e. all the abstraction principles whose main operator deductively implies part whole. And thus the inconsistency of BL5 is not an isolated fact. Of course, this would be a very disappointing result if it turned out that the only abstraction operator implying part whole is basic law 5. But this is not so. And in Mancosu and Siskin, we show that there are infinitely many abstraction operators that deductively imply part whole. By theorem 2.2, they are all inconsistent. Now, one can also ask whether all inconsistent abstraction principles satisfy part whole. And that would have been really nice. And that's what I was hoping to get, really. But in fact, this turns out not to be the case, as there are inconsistent abstraction principles that do not satisfy part whole. But that would take too long. And now I'm going to move on. And in fact, for the second application, given that I see that the time is going faster than I thought, I will only tell you that applications of the techniques used in this paper were used in this paper I published in the Review of Symbolic Logic with Shapiro and Siskin to also look at versions of choice principles in second-order logic. Just to give you a sense of what the complication is that when you think about the axiom of choice in and the well-ordering principle in ordinary set theory, basically what you say is that the axiom of choice, which allows you to pick from an arbitrary set of subsets an individual element, turns out to be equivalent to the well-ordering principle. But if you want to state the theorem, right, what you have to do is to say something like, for every set X, there is a covering function for X, which is just a choice function, if and only if X can be well-ordered. And when you do such a thing in second-order logic, you need to quantify over discovering functions that takes you from the power set of X into X itself. Now, that requires third-order logic. And so the question is, if you are in second-order logic, you cannot even state the equivalence in full generality. You can state in pure second-order logic what it means for a relation for a set to be well-ordered. That can be done in pure second-order logic, but this quantification over covering functions or choice functions is something you don't have. So what we do is to create a situation which is analogous to the one you have in neologicism when you add just one function that in the case of neologicism can be the abstraction operator, but here we add just one function that is going to give us a choice principle on the domain. And what we show is that if you then define the choice, here is the statement of choice, for every set X, if that set is non-empty, then you can pick an element that falls under X. And the two main results are that in an extension of pure second order logic, just with a delta function in the language and the choice axiom, you can prove the well-ordering statement, which can be stated in pure second order logic. And the other thing, though, is that in a way, we also show that the well-ordering principle is the strongest choice principle you can have in pure second order logic. And this is given by the fact that when you add the extra constant delta to second order logic and you add choice, you end up with a conservative extension of second order logic plus the well-ordering principle. Okay, this is a little fast, but I want to get to the probability material. Okay, so this is the last application. Let me start from a few definitions. A measure mu in a probability space, omega b mu, satisfies Kolmogorov's axioms if, in fact, you have the usual normalization at 1, every set in B is greater than or equal to 0, and then, of course, you have countable additivity. The two notions that are important for the results that I will state are regularity. Mu is regular if mu of A equals 0 implies that A must be the empty set for any A in the class B. And totality means that, in fact, B coincides with the full power set of omega. Now, regularity, expressed set theoretically, is the request that only logical contradictions, i.e. the empty set, get assigned probability 0. It states that no possible event can receive a probability 0 of occurring. And totality, on the other hand, requires that every subset of the sample space omega is measurable, i.e. it has a probability value. Now, it is well known that both regularity and totality fail for many standard Kolmogorovian probability functions. The failure of regularity and totality in the Kolmogorovian case, though, raises the issue of whether there exist theorems relating regularity and totality that can be stated in more general terms and that apply beyond the context of Kolmogorovian probability. For instance, the failure of totality in the Lebesgue measure uses countable additivity. What happens, for instance, if we weaken our probability functions to finitely additive functions? For instance, Banach in 1923 constructed a total finitely additive and translation invariant probability measure on 0, 1. But of course, that measure is not regular. Now, philosophers of probability have devoted quite a bit of attention to regularity, and that's because it comes up in all kinds of issues related, for instance, to the definition of conditional probability, update, revision update. So when you are learning new evidence of maybe extremely unlikely facts that were given probability 0 to begin with, suppose they come to occur, how do you update your beliefs? Well, that calls for conditional probability, and that's gonna lead you to dividing by 0. So that's annoying. You'd like some, possibilities of not having to divide by 0, for instance. So the discussion has recently been revitalized by the emergence of powerful infinitesimalist approaches to probability theory. For instance, in Benchi's work from 2013 and 18, which seem to open new possibilities for the defense of regularity by using infinitesimals in the range of the probability function. So this calls for an extension of the standard Kolmogorov setup, because the range is not going to be the standard interval 0, 1, but it's going to include now infinitesimals. But some philosophers have found this attempt to save regularity wanting. In particular, Williamson, Isvaran, and Hayek have claimed that the use of infinitesimals is not a satisfactory way of implementing regularity as a constraint on rational credences. For those of you not into this area, rational credences are just beliefs which have been assigned a certain numerical value in terms of probability. For instance, Williamson provides a thought experiment with countably infinite sequences of coin tosses and claims that even with infinitesimal at our disposal, the probability of such a sequence remains 0. And yet, such a sequence is possible. Meanwhile, Isver and Hayek argue that some of the issues for orthodox Bayesianism, which is the standard kind of approach in this area of formal epistemology that uses probability theory, created by the failure of regularity, are best addressed by a revision of orthodox Bayesianism altogether. In particular, not starting with a probability function that is defined on single events, but rather to take the notion of conditional probability as basic as it happens when one uses Popper functions, for instance. Now, in connection to the introduction of infinitesimals as a solution to the regularity problem in standard probability theory, the formal results discussed in the literature on the topic can be roughly divided into two categories. On the one hand, there are existing theorems that establish that under certain conditions on the sample space omega and the range of probabilities V, regular probability measures from the full power set of omega to V can be constructed. And on the other hand, we have impossibility theorems, which identify conditions on omega and V under which there can be no regular probability measure from P of omega to V. As an example of an existing theorem, consider the alternative approach to probability theory inspired by no standard analysis, namely the non-Archimedean probability theory, NAP, developed by Benchi and others. The main advantage of NAP over classical probability theory is that one can construct for any set omega a total and regular probability measure on the full power set of omega, whose codomain is a hyperreal extension of size to the cardinality of omega. So here is one typical theorem, existence theorem. For any infinite set omega, there is a total, regular, finitely additive probability measure mu from P of omega into this very complex object, which is the set of functions for omega to R modulo a finite ideal. In other words, given any sample space of cardinality kappa, one can always obtain a total and regular probability measure on P of omega by finding an appropriate hyperreal field of cardinality 2 to the kappa. By contrast, the best impossibility results existing in the literature until the work that Massa and I did could be found in Pras 2013. Now, Pras focuses on the size of the sample space. It shows that whenever omega is strictly larger in cardinality than the range of a probability measure mu, then mu cannot be regular. But all of Pras's results in his article require omega to be bigger in cardinality than the range of the probability function. And our main contribution to the existing literature is an improvement of Pras's impossibility theorem. Using a notion of generalized probability measure inspired from Pras's stating, we established the following. For any generalized probability range, don't worry about the, as it were, the type of structure is just a monoid. And for any set such that the cardinality of omega is is greater or equal to the cardinality of the range, there is no total regular V probability measure for omega. This theorem is a clear strengthening of Pras's results, since it establishes that the assumption that the cardinality of omega is strictly greater than the cardinality of V can be weakened to greater than or equal to. So we also combine our novel impossibility theorem with existing theorems, such as the one in Bench and others, to address the following question. Given a sample space omega and a cardinal kappa, is there a generalized probability range V of size kappa and a regular generalized V probability measure defined on P of omega? And we show that under the assumption of the generalized continuum hypothesis, the conjunction of the non-existent theorems and our impossibility result yields a complete answer to the question we posed above. So here is the theorem: let kappa be a cardinal and omega a set. Then there is a hyperreal field of size kappa and a total and regular finitely additive probability measure mu from P of omega into R, if and only if the size of omega is strictly less than kappa. Now, the generalized continuum hypothesis here is, as it were, only necessary to give the theorem this super nice form as an if and only if. If you don't assume that, we still have a theorem. It's just that it's a slightly a little more complicated to state. Okay, so now in the 2 minutes I have left, or 3, let me just mention why this stuff is related to Zermelo's theorem on part whole, which I haven't mentioned yet. As in the standard, as a standard in the literature on generalization of Kolmogorov setting, we start with the notion of a finitely additive measure, and probability measures are simply spatial cases. So a finitely additive measure is a triplo omega, mu. Omega is a non-empty set. I is an algebra of sets over omega closed under finite unions and complements, and mu is an additive function from 0 to infinity. We say it's a probability measure where when mu takes values in the interval, in the unit interval. So the range of mu is included in the standard interval 0, 1, and mu of omega gets normalized to 1. So here is the key and crucial aspect that relates what I've told you so far to part whole. It turns out that a finitely additive measure, omega a mu, satisfies part whole. This is the definition. If for all a and b in A, such that A is strictly included in B, we have that the measure of A is strictly less than the measure of B. And then one proves that, in fact, part whole and regularity are basically two sides of the same coin. Let mu, this is the lemma, let mu from P of omega into 0, 1 be a finitely additive probability measure. Then mu satisfies regularity if and only if mu satisfies part whole. Okay, I'm not giving you any of the proofs, but they're not hard, actually. So recall our theorem, Zermelo's theorem, right? Take an arbitrary set and any arbitrary function from P of x into x. Then there are sets A and B, such that A is strictly included in B, but f of A is equal to f of B. Now, in probability theory, often we are in situations in which we're sending the full power set of a set X, the set of events, into the very same set. And so here is one immediate application of this result. If you take X to be the standard interval 0, 1, and let mu to be a finitely additive measure from P of 0, 1 into 0, 1, then you know that mu cannot be regular. Why? Well, because it defeats part whole by Zermelo's theorem. But now you see what our problem was at the beginning. We realized this fact immediately. Problem is that this is a very narrow application in probability theory. You don't always have that the sample space, right, can be seen as identical to the range. So theorem 4.5 only uses a special case of Zermelo's theorem, namely the one when the sample space in the codomain of the function f is the unit interval. But what we have been able to do is to generalize Zermelo's theorem in such a way as to overcome this restriction by extending the results to wider classes of sample spaces and to generalize codomains, for instance, non-Archimedean codomains. And the generalization of that is the content of the main theorem I gave you before as 4.2. And here I stop. Thank you very much.
Thanks, Professor Mancosu, for his nice talk. And are there questions or comments?
A curiosity. In your main theorem, the set of hyperreal numbers that you construct.
This one?
Yes. Can this be an ultra power, or is a more general structure like limit ultra powers? So what I mean is this R a straight ultra power of R, or a more general construction you use there?
Well, you just use an ultra power, but you have to then mod it. I mean, if you go back to the original result by Vieri, by a special type of ultra filter.
Okay.
Yeah, or
so
an ideal, actually, a fine ideal in that case.
No, I was wondering if you were using more general constructions. You just take an ultra power, and you choose carefully the ultra filter.
Yeah, but those are the existence theorems, and we don't really meddle with that. We're into possibility results. So we show that certain structures cannot exist under certain conditions. Okay, thank you. So we don't really provide existence theorems. Those we take from the literature, in particular from Bench's work. Yeah.
Are there comments or notes? If not, we thank you, Professor Mancosu, again.
Thank you very much. And I regret not being able to follow the other talks because I'm teaching today. So, but good. I wish you all the best for the continuation of the conference.
Thank you.